Radioactivity. Oh, the last one, I promise. Last lecture, I promise. Radioactivity was discovered by Marie Curie in the 1900s. She was able to isolate radium from a pitch blende which contained uranium ore, and then use acid and filtered and used acid and filtered and acid and filtered and did that a bunch of times. They didn't actually know at the time how bad radioactivity was and how dangerous it was, so she slept with like a chunk of it next to her bed so she could take readings at night and stuff, and she thought it was cool because it is cool. But it eventually caused cancer and she did die from that. So there is a link I'm going to post in Google Classroom that is just a short couple-minute video over her experiments and a little bit about who she was in case you're interested, because she is a very fascinating and smart individual. All right, so sometimes, most times, all the time really, radioactive decay doesn't happen in one step. It happens in multiple. So like uranium doesn't just go straight to lead and then be done. It goes through a bunch of different decays and then slowly works its way down to something more stable. And the goal of the nucleus in all of these is to create a non-radioactive form that's much more stable than the original. So here are a couple practice problems in case you need some more practice. I'm not going to ask that you do them. They're just here in case you need more. If you have any troubles or need any help with it, please let me know, and I would be more than happy to go through some of the examples with you. Half-life is the last thing that I want to talk about. The half-life is the time required for half of the original sample of the nuclei to decay. So if we, for example, have 1,000 nuclei and 7.5 days later the sample has 500 nuclei, the half-life of this sample then is 7.5 days. Because we went from 1,000, divide that in half to 5, it took 500. It took 7.5 days to get there. So then if you had those 500 nuclei, waited another 7.5 days, it would go down to 250, right? And it just keeps going in halves from there. So a given sample of a radioactive nuclei will always have the same half-life, right? So if my carbon is radioactive, its half-life, no matter what, is always going to be the same. Same thing with uranium, same thing with all of them. All of their half-lives are the same for that element. So a sample problem here. How long would it take for a sample containing 1 mole of radium-223 to reach a point where it contains only 0.25 moles of radium-223 if the half-life of radium is 12 days? So your first thought is to think, I'm going from 1 mole, a half-life is going to take me to half a mole, so that's 12 days. And then I've got half a mole going to 0.25 moles, so a quarter of a mole. That's another 12 days. So since I went through 2 iterations of that, the first one being 12, the second one being another 12, my total would be 24. So I've got 24 days going from 1 mole to 0.25 moles. This is a practice problem. It's got a lot of words, but I'm going to leave it up here for a little bit. I'll read through it, and then I would like you to post your response in Google Classroom. Watches with the numerals that glow in the dark were used making radioactive radium in the paint. Assume that to make the number 3, a sample of paint contains 8.0 times 10 to the negative 7 moles of radium-228. This watch was then put in a drawer and forgotten about for a long time. After its discovery, a person analyzes the paint and finds 1.0 times 10 to the negative 7th moles of radium-228. How much time has elapsed if it has a half-life of 6.7 years? So first step, figure out how many half-lives it took to get down from 8 to the 1 times 10 to the negative 7th, and then add up your 6.7 years. Make sure to post those in Google Classroom, please. Last thing I wanted to talk about was the usefulness of radioactivity. So now we use radioactivity in radioactive dating. That can be dating fossils, it can be dating meteorites. Just finding out how old something is based on that relative decay because it happens at a very steady rate. We use them to treat cancer. We use them to treat medical tests, just like what we talked about in the beginning. We also look at medical and biological function and the research on how different proteins or different RNA strands, whatever, can function within the body using the radioactivity. And then it's also used in your everyday life. The sun is a huge source of radioactivity. That's its whole nuclear process in there. Nuclear power plants, and again, just research. If you have any questions, make sure you ask.